So our next speaker is Moses Ganardi, who's gonna talk about balancing straight line programs.
Okay, so this is joint work with Markus Lohrey and Artur. And the topic of this talk is grammar-based compression. So this is a mathematical formalism for lossless compression. And what makes it so attractive is not only that we have a compact representation of data, but we also have efficient algorithms which work directly on the compressed representation. So we want to avoid unpacking the data first and then have some algorithms working on them, but we want to directly work on the compressed representation. And grammar-based compression is such a formalism where this has been quite successful. So here's a definition. A straight line program, or short SLP, is simply a context-free grammar which produces exactly one string. And so we view this SLP or this grammar as a compressed representation of the string. So let's start with simple examples. So here we have a couple of rules, and I claim that they produce, so the left one produces an exponentially long string. So you have these variables, an to a0, an goes to an minus 1, an minus 1, an minus 1 goes to n minus 2, n minus 2. Finally, a0 goes to a, and so it's not hard to see that these n rules produce a string of length 2 to the n. On the right-hand side, there's another example which produces the so-called nth Fibonacci word, and it is also exponential length. So here's a more syntactic definition. So as you know, we can always assume Chomsky normal form in grammars. So an SLP over some alphabet sigma is a sequence of rules. Xi goes to alpha I, so we have n variables xi and n rules. And the alpha i's are either terminal symbols from sigma, or the concatenation of two variables xj, xk, where j and k must be bigger than I. So this ensures that the derivation is acyclic, so we produce exactly one string. So in general, I have three viewpoints of these SLPs. The first one being grammars, but we can also view them as graphs. So let's define the following directed acyclic graph, or short DAG, where we introduce for every variable in the grammar a node. And, well, the terminal nodes are the variables which derive two terminal symbols. These are the sinks in the DAG. And the other rules, well, they correspond to nodes which have a left edge and a right edge, pointing to the variables on the right-hand side. And finally, we have, of course, the derivation tree of the grammar, or the path tree. And here we can already see the string labeling the leaves. So here it's a 1, 0, 1, 1, 0. This is the produced string by the grammar. And so you can also view the DAG as a compact representation of the derivation tree. You simply merge all isomorphic subtrees to be a single node. And so this DAG is a compact representation for this derivation tree. And so we will actually switch between these viewpoints throughout the talk. Okay, straight line programs, as we have seen, they can represent exponentially long strings, and they're somehow good in practice and in theory. So there have been implementations, in particular repair, which turn out to be quite fast and produce small grammars or small SLPs for practical data. But there are a lot of theoretical results also. For example, you might know the LZ77 compression, and there's a strong relation between those formalisms. So you can always convert an LZ77 compression into a straight line program with only a small overhead. Yes, and straight line programs, so we will consider mostly strings, but they have also been extended to trees and graphs. So there are many efficient algorithms on SLP compressed strings, as I said. For example, the question, given two SLPs, do they produce the same string? This is solvable in polynomial time. This is a result by Plandowski, which is not obvious at all because they are possibly exponentially long strings. And other problems which you can think of on strings have been studied, like substring extraction, pattern matching, or running automata on strings have been also studied in this SLP compressed world. So if you study algorithms on SLPs, there are mainly two important parameters which influence the complexity of these algorithms, which are size and depth. So the size is simply, well, the number of variables if you're in Chomsky normal form, but well, if you allow also longer rules, then you should count the total length of all rules. But another important parameter is depth. And by depth, I mean the depth of the derivation tree of this grammar. So there's a result by Ritter and also by Charikar that says, given an SLPG for a string of length n, and I will always denote the string length by capital N to remember that this can be exponentially long in the grammar size, you can compute an equivalent SLP of logarithmic depth, and the size is bigger by a factor of log n. So this is logarithmic in the string length n. And actually, it has been an open problem for quite a while in this field, whether this logarithmic blow-up in the size can be avoided. And so in this paper, we prove this in the positive. So the main theorem is, given an SLPG for a string of length n, then one can compute in linear time an equivalent SLP of logarithmic depth and size only blow up by a constant factor. So this is some kind of depth reduction or balancing theorem. And so before I comment on the proof, let me try to convince you why this is interesting. So some application. So let's consider the following easy problem, the random access problem. So I give you a SLP G for a string of length n and some position in the string. And the task is to output the ith symbol of the string. So there's a very simple solution, which does the following. Well, first, we want to compute the length of every variable. And we can do this in linear time in a bottom-up fashion. We know the terminal variables, they have length 1. And, well, if we have a rule of the form A goes to BC, then we simply sum up B and C's length to get the length of A. And then to query the ith position in, let's say, some variable A, where we look at the rule, so let's say A goes to BC, and because we know the length of B and C, we know where to go next, right? So either we go to the ith symbol of B, or we go to the I minus bth position of C. So what is the complexity of this algorithm? Well, the pre-processing time is linear, so we only have to compute all these lengths. And, well, we assume that a single memory cell can store the length of such a variable. So this is a standard assumption that we have bit length log n of the words. So we can also store all these numbers in linear space. But the query time, it's linear in the depth of the grammar, right? Because we go down a path in the derivation tree. And so a priori, this depth can be as large as the grammar itself. And so thanks to our new theorem, we can actually first make the grammar logarithmic depth and then apply this naive solution. So the corollary is that you can support log n random access time using only linear preprocessing time in space. So this result actually is not new. So this was already proved by Bille et al. But yeah, admittedly, their proof is more complicated and uses very sophisticated data structures. And our new proof is very elementary and does not use any fancy data structures. Later, I will give further applications for the balancing theorem. But now I want to show you how the proof is done. All right, so to recall, we want to show that we can always make an SLP to be logarithmic depth without blowing up the size too much. And we use two main tools. So the first thing is, as I said, we will view the SLP as a DAG. And we will decompose the DAG into a collection of disjoint paths. And this decomposition will have logarithmic depth in a certain sense. And the second tool is to have some kind of weighted version of the prefix sum algorithm. Okay, and I want to comment on both of these tools in the following. So there are, maybe let's not first talk about DAGs, but about trees. And there are many decompositions known in the literature which decompose a DAG into, a tree into paths. Maybe most famous is the heavy path decomposition. But we just chose this one, the centroid decomposition by Cole and Vishkin. So they only differ like in the small details. So what we do is we view, let's say, this binary tree, and we label each node by the leaf size and take the logarithm rounded down. So the leaf size is simply the number of leaves in the subtree rooted at that node, and we take the logarithm. So in other words, this is the unique number k, such that the leaf size is between 2 to the k and 2 to the k plus 1 minus 1. And so it has some nice properties. First thing, of course, this number is monotonic if you go down the tree. But also, if you have two siblings which are labeled by the same number, then the parent node must have a strictly larger number. So in particular, this means if we mark those edges which connect with the same label, and I will call these centroid edges, then every node has at most one outgoing edge. Right? So what we get now is a decomposition of the tree into disjoint paths, possibly of length 0. These are the ones which are not participating in any path, but well, they are paths of length 0. Yeah, we get this decomposition, and the main property is that every path from the root to some leaf only traverses log n many of these paths, or log n many of these non-centroid edges. Of course, because the labels are bounded by log n. All right, so we can try to apply the same approach to, let's say, the DAG of our SLP, but then we run into some problems. So what we should do is maybe we label each node by the logarithm of the leaf size of the node, but well, what is the leaf size? Well, I propose to take the number of paths to sinks. So we take some node, and you can also view it as unfolding the DAG into a tree and then counting the number of leaves. Okay, so this could look something like this. But now we have the problem that, okay, still from every node we have at most one outgoing edge, but now there can be many incoming edges, right? Because we are in a DAG. So we will try to fix this, but still we have this good property that every path from the source to some sink only traverses log n many non-centroid edges. And here n is not the size of the DAG, but the total number of paths from some source to some sink. All right, so we will try to make these trees again into paths by simply making it symmetric. So this is a very simple idea. So let's take a DAG, and for a node, we define the out number, which is simply the number of paths from that particular node to some sink, and the in number, which is the number of paths from some source to, or from this source to that node. And now what we do is we label each node by the pair of these two numbers and take the logarithm. Right? And now, well, this labeling is again monotonic in the sense that if we go down in the DAG, then the out number goes down and the in number goes up. And well, it's not hard to show that the following holds. So if you now consider the edges which label nodes with the same label, nodes with the same label, which I will define as this symmetric centroid decomposition edges, then they form a disjoint union of these centroid paths. Again, possibly of length 0. And every source to sink path traverses at most 2 times log n many edges from which are not centroid edges. So this is good. Now we have decomposed our DAG into disjoint paths, and there are only like log n of them on top of each other. So what remains to do is we need to somehow make these centroid paths small depth. So this could look something like this. Let's just zoom in on a single one. And the problem is that they can be actually quite long. They can be as long as the grammar itself. So what we do is let's now look at the variables which hang on the left-hand side. Let's call them Li. And the variables that hang from the right-hand side, let's call them Ri. And what we can see is that every variable on the centroid path actually is a composition or a concatenation of a suffix of the Li's and a prefix of the Ri's. Right? So what we should do is, okay, I mean, just combining the suffixes and the prefixes is just one extra step. So let's just focus on the suffixes. So we are successful if we proceed in producing all suffixes somehow in small depth. And then similarly for the prefixes, and then we just have to combine them. This is just one single step. This does not blow up the size or the depth too much. So the remaining problem is the following. We're given a string L1 to Ln, and so these Li's are the variables which hang or which branch off to the left-hand side, but now I view them as single symbols. So given such a string of length little n, we want to construct a grammar or an SLP of linear size which contains suffix variables which produce all suffixes. So suffix variables S1 to Sn, where Si produces the ith suffix. And also it should somehow have a small depth, but I will comment on that later. So of course there's a simple solution. Just produce them all sequentially. Right? The ith suffix is the ith symbol together with the I-1 suffix. This has linear size, but of course the depth is also linear, and so this is too large. Now, the classical parallel prefix sum algorithm actually achieves this in linear size and logarithmic depth. But this is also still too much because, well, we have in total log capital N of these centroid paths on top of each other, and if in each one we take log n depth, log small n, then this can be up as large as log n squared. So this is also not what we want. So what we do is, to solve this problem, is we view this L1 to Ln as a weighted string, right? So every Li produces some string of some length, and this is the weight that we assign to the symbol. And so the main theorem that we show is, given such a weighted string, L1 to Ln, one can compute an SLP in linear time such that the following holds. The SLP has linear size, it has these suffix variables which produce the suffixes, and now if you consider a derivation path from a suffix variable si to some symbol lj, then the length is bounded by order of 1 plus log of the depth of the suffix variable minus log of the symbol. Or in other words, well, what one also could try to do is to form a strongly balanced grammar, where in every step the weight decreases by, or goes down by a constant factor. This is not what we achieve, but this is some kind of, how do you call it? Like a along this path, this holds, yeah? So why does it help us? Well, if we now consider a derivation path in the final SLP, then it consists of these log n steps, which are contributed by the non-centroid edges. So like if we jump from one centroid path to another. And now if we count the number of steps that we take on the centroid paths, well, then we get a sum over all these terms, 1 plus log si minus log lj. And now because this is a telescoping sum, because the lj's are always bigger than the next si's, all these terms cancel out, and in the end we get magically this log n number. So this is basically the main theorem that we need to show, and as I said, this is some kind of weighted version of the prefix sum algorithm. All right, so let me comment on applications and extensions. So using the balancing theorem, we can reprove or even improve many algorithmic results on SLP compressed strings. So besides random access, we have rank and select, labeled successor queries, computing fingerprints, and range minimum queries. Let me also mention that actually we can reduce for random access the query time to log n over log n by increasing the space a bit by this log n to the epsilon factor. So this is actually was also already known previously, but using our balancing theorem, we get a cleaner proof of this result. And as I said, SLPs have also been extended to trees. So we get formalisms called tree straight line programs, forest straight line programs, or top decks. And for free, we get all this balancing theorem also for these formalisms. So given one of these tree formalisms, we can always reduce the depth to be logarithmic in the size of the tree, of the forest, without blowing up the size too much. And actually, the most general result that we get is for circuits. So you can actually view SLPs as circuits over the free monoid, right? The elements are words over some alphabet, and the operation that you have is concatenation. And this is the free monoid, and actually we can prove something for general algebras. So suppose you have an algebra which has some good properties, which we call finite subsumption based, and I will not define this here now. Then you can always make a circuit over this algebra, logarithmic depth. And here, so log n, and n here means the unfolded size. So again, we count the number of paths from the output gate to any input gates. All right, so let me conclude the talk. So this was our theorem. We can always, in linear time, reduce the depth of SLPs to be logarithmic. And so in particular, the last one, the result here on circuits, maybe remind some of you of the known depth reduction results in algebraic circuit complexity. And so actually our results, so our result and their result is actually orthogonal, but we're still wondering whether there can be some kind of bigger framework for comparing these results. So I also talked already about this stronger balanceless notation. So maybe can we reduce or replace logarithmic depth by alpha balanceness, which means that in every step we reduce the size by a factor of alpha. And a third question, can we also support random access queries in linear space and query time log n over log n? So now it's only known that the space must be slightly above linear. Okay, thank you.
Do we have any questions? Let's thank Moses again.